The scientific method. In science, we try to answer questions objectively. We need to find the answer to questions that are not subjective in nature, such as what's the best flavor of ice cream? It has to be a question that can be answered objectively. When you find a question in science that can be answered objectively, then what you do is you use a specific method by which to solve that problem. This method is called the scientific method, and it's defined as an organized plan for gathering, organizing, and communicating information. And the goal of using the scientific method is to solve a problem or understand an event. And the steps come in a distinct order because that helps to give credence to the science behind what you're doing. So the steps are, as we said, are in order. So the first step would be to make observations and to identify a problem. So if I have a problem, for example, I'm driving down the road. We live in Palmyra. We're around lots of farmland, and as I drive down the road, I see that one farmer has much better corn growing than, say, another farmer. Okay? If I ask myself the question, why is that farmer's corn growing better than this farmer's corn? The first thing I want to do, if I'm going to use the scientific method to find the answer to that problem, is I'm going to make observations first. I might look and see that the corn is being grown in the same environment. I may look to see what kind of seeds are being used, what kinds of fertilizer are being used, how the land is being plowed. I try to gather as much information as possible, and then I identify a problem. Why is the corn growing better for one farmer than for another, for example? The second step in the scientific method is to form a hypothesis or make an educated guess to answer the problem. So a hypothesis is an educated guess. I've gathered some information, I've stated a problem, and from that information that I've gathered, I'm going to give my proposed solution to that problem. But it is backed by the observations that I've already made. And this is a hypothesis that must also be testable. Okay, it can't be a hypothesis like little green men from Mars are coming down and they are helping the corn to grow better. Unless I can show that little green men are coming down and helping the corn of one farmer over another, that's not a testable hypothesis. Okay? So maybe my hypothesis might be, after I've gathered all my data, that it's since the corn is being grown in the same environment, and it looks like many of the farmers are using the same types of seed, and they're using the same cultivating methods. But the only difference that I'm seeing is that one farmer is using a different kind of fertilizer than another farmer. So I'm going to say that it's the type of fertilizer that is causing the differences in growth in the corn. Okay, step 3 is to actually test your hypothesis. And this is done, if possible, in a controlled environment, an environment that the experimenter can control. We usually try to do this in a laboratory, for example. But, if it's a natural type of science, it might not necessarily be done in the confines of a laboratory. So let's take a look at some of the pieces of the testing of the hypothesis. The first thing is that whenever I'm testing my hypothesis, I have to have variables. These are parts of an experiment that can be changed. So if I'm looking at my question, why is the corn growing better for some farmers other than others, I gathered some information, and I'm looking at the soil and so forth. Soil is something that can be changed. The type of corn seed can be changed. These are all variables. Now, a variable that gets changed by the experimenter is called the independent variable. So my hypothesis was that it's the type of fertilizer. So if I'm the experimenter, the only thing that I want to change in my experiment from one setup to the next would be the thing that I'm testing. In my case, my hypothesis is that it's fertilizer that's causing the change in the growth of the corn. So fertilizer would be my independent variable. Another variable may change because I've changed my independent variable. So depending upon the type of fertilizer might show me the type of growth that I'm getting in my corn. The corn's growing better in, let's say, manure. The corn's growing better in a commercial fertilizer. The corn's growing better with no fertilizer at all, for example. So if I'm changing the type of fertilizer, that's my independent variable, then the growth of the corn, or how well the corn grows, becomes my dependent variable. The growth of the corn is dependent upon the fertilizer. That's what the thing that I'm testing. So therefore, any other variable, any other thing that I could possibly change must not be changed during the test. And I call these things control variables. So if I'm setting up a test to test fertilizer, fertilizer is the only thing that I change. I'm going to use the same pots, the same number of pots, the same soil, the same amount of soil, the same seeds, the same amount of seeds, the same amount of moisture. I'm going to water them all the same. I'm going to put them all in the same environment. They're all going to get the same type of light. All of these things that I am controlling and keeping the same are called control variables. Now, why do I do that? The reason that I do that is because I want to make sure that the differences in corn growth, that difference in dependent variable that I'm seeing, is only coming from my independent variable, the thing that I'm testing. Okay? I want to make sure that if I have different kinds of seeds and different kinds of fertilizer, how can I tell if the differences in corn that I'm seeing, the difference of that dependent variable, how can I tell if that's coming from the type of seed or from the fertilizer? This way, if everything is kept the same except for my fertilizer, then I know that the differences that I'm seeing are coming from the fertilizer. So I'm only changing my independent variable, the thing that I'm testing, and the growth of the corn, something that's dependent upon the thing that I'm changing. Everything else stays the same. Those are control variables. Okay, and sometimes we also like to have control groups as well. A good test also includes a group that does not change any variables, okay, and allows the experimenter to kind of observe things that I may have missed or may have not realized. So let's say, for example, I'm setting up my test to test, why is the corn growing better for some farmers rather than others. I've determined that that's coming from fertilizer, and so I might set up maybe 10 pots with the, well, I'd say 30 pots, all with the same amount of dirt. 10 of them have no fertilizer at all. 10 of them have manure. 10 of them have a commercial type fertilizer. They all have this, they're all the same kind of pots. They're all the same amount of soil. They're all the same type of corn seeds being planted. They're all the same amount of water, getting the same amount of light. I've controlled all my variables other than my independent variable and, of course, my dependent variable. And maybe what I want to do is I want to just have a few pots with no soil at all in them, or just the seeds are there. And I might see when I do that hey, these seeds are infested with bugs, and I'm not getting any kind of growth in any of my pots, and some of the growth is sporadic, but it's because they're the corn that I chose to use happens to be infested with bugs. Oh dear, it helps me to see that there are some parameters there that I didn't take into account. Maybe I have to spray my whole area with insecticide before I can, the same amount of insecticide on all things, so that I can see that the growth of the plant isn't coming from insects. Or maybe I just have manure but no seeds in the pot, and then I see, oh my goodness, my pots with manure and no corn seeds in them are still growing corn. Why is that? See, I'm a girl from the city. I didn't realize that cows eat corn. Cows make manure, and they don't always grind up all that corn, and some of that corn's coming out in their manure, and so I've got all of this corn in there that I didn't realize, and that's skewing my results. I'm getting much better growth of corn, but of course maybe I have double the corn in my manure pots because of this phenomenon. So I did realize I'm going to have to take and sift all that manure and make sure there's no corn in it. So when you have control groups like that, it helps you to look for factors that maybe as an experimenter you didn't think of, you didn't have the background information for, but are caught by your control groups. So once I have made observations, stated my problem, I've formed my hypothesis, I've tested my hypothesis, I've gathered my data, and from my data then I would draw conclusions. That's my fourth step. So I've tested and I've gathered my data, and I might use a statistical program, look over my data. I might put it in a graph so I can see it visually. I am going to look at my data and determine, oh my goodness, the growth is so much better in the manure, even better than the commercial brand, even better than no fertilizer at all, my organic corn that I grew there. I might draw the conclusion that the corn grows best when you use manure on the fields rather than a commercial fertilizer or no fertilizer at all. That's my conclusion. Now, a conclusion may prove or disprove my hypothesis. And in science, the nice thing about science is it's okay to be wrong. So you're like, oh, my hypothesis was it's the fertilizer, and this time I happen to be right. But what if my hypothesis would have been that it's the type of corn, and I found that that wasn't true? I just say, oh, well, I can revise my hypothesis, I can pick another variable, or I can change my question completely, lead me to a different question. Okay? Step 5 then is to develop a theory. Now, a hypothesis is an educated guess. A theory is a well-tested hypothesis, and it's something that I'm seeing as a natural trend in the world. Okay, so let's say that I go to the farm show and I present this to all the farmers. Farmers, quit wasting your money on that commercial fertilizer. Have I got the thing for you? Manure's the way to go. Your cows are making it for free. Put it on your fields. And the farmers are all riled up and they're like, all right, this is what we're going to do. And I have all of these students at Penn State go out, and I have them go all across the state, and I have them collect data. I have all the farmers in Pennsylvania break their fields up into thirds, and a third of them grow their corn using commercial fertilizer. A third of them, their corn is grown with manure, and a third of it's grown with nothing at all. And we're continuing to see the same results that I saw. Then I'm going to develop a theory, Mrs. Mateer's theory of growing corn using manure. Okay, I'm known as Dr. Manure in the scientific journals, and I've developed this theory of the growing corn using manure. And it's saying basically that we've tested this over and over again, season after season, and we do see that manure is the best way to grow corn. Then I have a theory about corn growth in manure. Okay? As new tests support theories, they become stronger. So year after year after year, as the data is compiled and as these tests are being made, my theory is becoming stronger and stronger. I'm hailed by farmers because I'm saving them millions of dollars. No, thank you. Your cows are what gave me this great idea. Thank you. Just, no need to throw money. I understand. I'm awesome. Okay? If the tests fail to support the theory, then maybe I have to revise my theory, as I said before. Maybe as more and more data is coming in, I'm seeing that it's really only white corn that this is a factor for. So when do we go from being a theory to a law? Like, why do we have the law of gravity, but we have the theory of evolution? Okay? So when I have a hypothesis that's been tested repeatedly and never been contradicted, and is what I'm seeing to be happening all the time, so that it's genuinely given as true. It can't be proven, but it's never been misproven. It becomes a law. Okay, so how many of you got up this morning and you said to yourself, oh my goodness, I'm afraid to get out of bed because I might step out of bed and I'll just fly off the earth? that law of gravity. I'm not so sure about that law of gravity. I mean, you've never had that thought because every time you got out of bed, ever since you can remember, your feet have hit the floor and you didn't fly out into space because gravity has pulled you to the earth. Okay? That's why the law of gravity is called a scientific law. No one has ever flown off the earth by their own free will, other than, we force ourselves into space using rockets, but we never just like all of a sudden, oh my goodness, floated off into space and died. Okay? So we can call Newton's law of gravity a scientific law because it's never been disproven and it's been proven repeatedly over history. Okay? The theory of evolution is still called a theory and has not been called a law because we have not gathered enough information at this time to say, I'm pretty well sure that that's what's happening. Okay? So a law is summarizing a pattern that we're seeing in nature that's never contradicted. Okay? Now, scientific theory and scientific law are very different from scientific models. Scientific theory and scientific law have been tested and retested using the scientific method so that we're assuming that these concepts are true, and we will continue to assume that they're true until they're disproven. Models, on the other hand, are representations of objects and events that we use to describe phenomena that we see in nature. Okay? Models are used to help us understand things that we can't directly observe. So I want to go and I want to test a tornado, and I finally find a tornado. They're very hard to study because you never know when they're going to pop up, but I happen to be at the right place in the right time, and I put my little instrument on, oh, dang it blew away. It's very hard to study a tornado. What I can do is create the model of a tornado on a computer and show a simulation of what would happen. Or I can actually create a little tornado out of wind, a little wind tunnel tornado in the laboratory. Okay? But be very careful because a model, it's really hard to get all of the parameters if you are making a representation of something in nature. You might think you have all the parameters put in, but you don't. You don't have any control group there. So it's hard to say what parameters you could have missed out on. I thought the plague was going to wipe us out in 4 years, but it was much more virulent than I thought, and we all died off in a matter of days, for instance. Okay? So scientific models may be changed as we get new ideas and new information as technology improves, and as we look at all the parameters more closely, our ideas are changed. And that's the nice thing about the way that science works, is that it's okay to be wrong. I had a science teacher that had a big sign that says, half of everything I'm telling you is a lie. I just don't know which half. And that's very true in science. Okay? If you look at a book in the 1960s dealing with Mars, they used to talk about forests on Mars, dense vegetation that grows in seasons, and there's winters and there's summers. From looking at a telescope, that's what we thought we saw. As our telescopes got better, we realized, hey, we're not looking at seasons and snow. We're looking at arid ground and dust bowls and things. So there's no forests and vegetation on Mars, even though in the 1960s, astronomy books actually said that about Mars. So that's why everyone in the 60s was afraid that the Martians were going to come and destroy us, because they thought that there was life on Mars. And we said, there's no life on Mars. In the 80s and the 90s, we're like, psh, my bad, we were wrong. And then we send rovers to Mars, and maybe we will find life, and we'll have to reevaluate, hey, there's no life on Mars. Wait, there's bacteria on Mars. Maybe there is life on Mars after all. So that's the nice thing about science. As things, technologies improve and ideas improve, we can revise and prove and disprove our theories and laws. Okay, now I have already given you that example as I was talking. See if you can find an example in your textbook in which they are telling you about the scientific method, and they give you an example. Okay? So to recap, the scientific method, the major steps of the scientific method are to first make observations, and from those observations you identify a problem or to solve or a question to answer. After you identify your problem, you form a hypothesis, your best guess, your answer to the question, and it's an educated guess. After you provide your hypothesis, you test your hypothesis through experimentation, and from your experimentation, you form a conclusion. If your conclusion is correct, that conclusion can be further studied by other scientists and developed into a law or theory. And in doing so, in trying to formulate or develop a law or theory, you might actually open new questions. That might be the end of it. You end with your theory, or it might open new questions that start the process all over again. Sometimes your conclusions show that your hypothesis was incorrect. And if your hypothesis is incorrect, you can either discard your hypothesis or you can change parts of your hypothesis and retest. Discard your hypothesis altogether, test another variable, or change parts of your hypothesis, refine your hypothesis, and re-experiment. And hopefully those discards, changes, will lead you the next time to develop a law or a theory.